Welcome to CEE 592, Biological Processes in Environmental Engineering. In this course, we will dive into the fundamentals of biological processes, including energetics, stoichiometry, and kinetics, and use their mathematical description to model these processes. Because biological processes are most commonly used in wastewater treatment, in this first class, we will review why we treat wastewater, what is in our wastewater, and how we treat it. During our domestic activities, such as doing laundries, flushing toilets, washing dishes, and taking showers, we use clean water and add various constituents in it. Our industrial and agricultural activities also add a variety of constituents. These constituents, however, are parts of the natural carbon, nutrient, and energy cycles. As a simplified example of the cycles, let's say we eat a banana and convert part of its organic carbon to carbon dioxide, and utilize the energy generated during this reaction for our daily activities, such as heart pumping, muscle contraction, and so on. The part that we cannot digest, or the part that are used by our gut microbiome, eventually also gets converted to CO2 and released to the atmosphere. The plant uses solar energy to convert CO2 into new banana through photosynthesis. Hence, it's a full circle. And the same applies to all the constituents added to water, naturally or anthropogenically. But if these constituents are added to natural water bodies in large quantity and high concentrations, they can tip the delicate balance of the aquatic ecosystem. Because of a population growth, urbanization, and industrialization, we are creating hotspots of adding these constituents. This map shows the increase of population centers in the world in the past few decades. Each population center is responsible for adding a large amount of these constituents, and this trend is expected to keep growing in the future. A high flux of organic carbon in a water body can quickly deplete the dissolved oxygen, devastating the aquatic life. It is also a hotbed for pathogens, which endangers public health. High concentrations of nitrogen and phosphorus can cause algal bloom, which depletes oxygen as well, but also leads to toxicity caused by cyanotoxin due to the proliferation of cyanobacter during algal bloom. To mitigate those impacts, wastewater treatment is introduced. Even though there have been a focus shift towards transforming and recovering those constituents as resources, impact mitigation is still the primary goal. You can read more about the history of wastewater regulation in the McAfee-Natty book. The three major components in wastewater industry is the regulation, design and operation, and research and survey. The regulation applies discharge permissions that the design and operation parties need to abide to. New technologies are developed through research and can help achieve better treatment efficiency with lower cost. New methods developed by research and concerns brought up by research and survey can provide guidelines for regulations. Either to remove the constituents or recover them as resources through treatment processes, we need to understand what are these constituents. Because they are extremely complex and there are dozens of major ingredients just in banana, and there are a wide variety of food and drug and beverages we consume, cleaning products we use, microorganisms we shed, and their metabolic products. We need to summarize and categorize them based on the measurement and treatment methods that's available. These constituents are summarized to indicators that can be determined experimentally and that are pertinent to the treatment processes. We can categorize them into physical, inorganic chemical, organic chemical, and biological characteristics. One of the most commonly used characteristics is the oxygen demand. It measures the reducing power, which is the ability of a compound or a combination of compounds to donate electron. This can determine how much biomass will grow from these compounds or a combination of compounds in combination with yield, and how much electron acceptor is needed for their removal. It is an important indicator for biological treatment processes. The carbonaceous oxygen demand is the oxygen needed to oxidize the organic carbon to CO2, or carbon with the +4 oxidation state. The nitrogenous oxygen demand is the oxygen needed to oxidize organic nitrogen or ammonia to nitrate, or nitrogen with a +5 oxidation state. COD, or chemical oxygen demand, is the oxygen equivalent of dichromate that's needed to fully oxidize the organic carbon chemically. It is only carbonaceous as it does not convert ammonia to nitrate. BOD, or biological oxygen demand, is the oxygen that's needed to oxidize the organic carbon biologically. It is both carbonaceous and nitrogenous, as it converts ammonia to nitrate. Theoretical oxygen demand is the combination of all potential carbonaceous and nitrogenous oxygen demand, and is not commonly used in practice. This figure shows the relationship between COD and BOD. The carbonaceous COD is higher than the carbonaceous BOD, as some organic carbon that can be oxidized chemically are recalcitrant to biological oxidation. Based on the particle size, COD and BOD can be further categorized into particulate and soluble COD and BOD. In some cases, particulate COD and BOD can be further categorized into particulate and colloidal COD and BOD, based on their size. Alternatively, COD can also be divided based on its biodegradability. There are a few ways of calculating the COD of a given compound. You can use this general expression to calculate the amount of oxygen that's needed, or simply balance the equation as you know that carbon dioxide, ammonia, and water are the products. A quick example, so 1 mole of the empirical biomass, which is 113 grams, requires 5 mole of oxygen to fully oxidize, translating to a COD of 160 grams. Total solids are the dried solids after putting certain amount of solids in a 105 degrees Celsius oven, while the volatile solids are the part of the total solids that evaporates in a 550 degrees Celsius furnace, and it is the organic part of the solids. The inorganic matter left is ash. The suspended solids are determined the same way, but with the solids collected on the filter after filtering a certain amount of sample. Because the headwork and primary clarifier removed most of the solids before biological treatment processes, the solids in biological processes are mostly the biomass grown using the soluble organic matter as substrates. As mentioned before, nitrogen and phosphorus can cause eutrophication in susceptible water bodies at high concentrations. But they are also the essential nutrients for microbial growth. Too low of nitrogen and phosphorus concentrations can limit the growth of biomass in biological processes. Pathogens can pose danger to public health and therefore needs to be removed before discharging. Microbial community is still an active research area. its composition and activity can influence the reactor performance. This is a schematic of a typical wastewater treatment train that can remove and recover the constituents added to used water or wastewater. In brief, the bar screen and grit chamber in the headworks remove the large debris and inorganic particles like sands and grits. After settling the organic particles in the primary clarifier, the soluble organic matters are removed in the secondary or biological treatment processes, for which aeration basins are the most commonly used. In this process, oxygen is supplied so that the biomass convert the organic carbon to CO2 and use the energy generated during this reaction for growth and maintenance. The biomass or activated sludge are settled in the secondary clarifier to be recycled or wasted. The clean supernatant can go through a tertiary treatment such as filtration before being disinfected and discharged. The settled organic particle and the waste activated sludge are thickened and sent to anaerobic digestion to generate biogas that can be used to generate heat and electricity for the operation of the plant. The digested biosolids are dewatered and land applied or landfilled or incinerated. The treatment train can be categorized into physical, chemical, and biological processes. We will focus on the biological processes, study the energetics, stoichiometry, and kinetics, so that we can use mathematical equations to describe the reactor mass balance, therefore predict the reactor performance, including the effluent quality, oxygen demand, and biomass production. We will spend the first few weeks of the class on fundamentals, and then look into the theories of suspended growth reactors with those fundamentals. We will then apply these theories into practice, and finally repeat the process for the attached growth system.